Hello there, Course 3 math students. Mr. Rising here. Not feeling well today, but I didn't want to miss a good day of class, so I thought I would record a lecture from home this morning and post it. The nice thing about this is you can watch it live now, but if you need to go back and look at examples, you can do it anytime. My boys are looking at me like, hello, and it's all good. We're all working together here. Hey, this is lecture 8.6, Solving Systems of Equations. And this is what we've been leading up to. These are the real life problems that really take all your skills and bring them together into something meaningful. I'm following along in your book, and I highly recommend you do the same thing. If you need to pause the lecture, get your book out. It's not a bad idea. What we're trying to do with systems of equations, you're going to learn over the years, there's multiple ways to solve them. But one of the easiest ways that incorporates all these things that you've already done is simply graphing each equation. And where these equations meet is where you have solutions. And if the equations never meet, then you don't have a solution. And if the equations are right on top of each other, then you've got infinite solutions. And you're going to study this a lot more in algebra. But for right now, let's just read along for a second. You can verify the coordinates of the intersection algebraically. Right? When you have two equations, when you have two situations, and the example they give you in the textbook is airplanes. I'm going to give you a different example in just a moment. The idea is where these lines cross is a solution to both, right? So let's just jump into an example and I'll show you what I mean. Marin is 5 feet 9 inches and is growing at a rate of 1 inch per year. Now that's probably going to change in the next 6 years, but for right now she's growing an inch a year. Bergen is 5'7" and is growing at a rate of 2 inches per year. So that means Marin can dunk on Bergen. For now, but wait till they're both seniors in high school and it's going to be a different story. The question is, will Bergen ever be as tall as Marin? If so, after how long? Well, when I look at this equation, there's a constant rate of change, which means it's linear. It's a linear relationship, so I can make a linear equation. Let me use h, a variable h, as the height of Marin or the height of Bergen, and t is the time in years. So if I wanted to build an equation to model Marin's height, I'd say her height is equal to 1 inch per year, 1t, plus 69. Well, where did I get 69 from? Well, I just took 5 feet, 9 inches, and converted it entirely to inches. So 5 feet, 5 times 12 is 60. 60 plus 9 is 69. So Marin's starting height in this problem is 69 inches. Bergen, 5 times 12 is 60. 6 plus 7 is 67. His starting height is 67 inches. However, Bergen is starting at 67, but he's growing at 2 inches per year. Very cool. So now what I've done is I've created linear equations to model the height of Marin and Bergen. Now, Bergen here, there should also be an h. Let me just throw an h in here so you're not confused. I know sometimes I can be confusing. All right, so now that I have equations, the simplest way to solve this is simply to graph it. So check out. Now my graph isn't exactly perfect because I don't have all the lines, but I made a graph here, and on the bottom here are years, year 1, year 2, year 3. And up here I'm starting at 67, 68, 69. And when I graph each one of these equations, you can see that there's an intersection, that they actually cross right here after year 2. Because after year 2, Bergen would be 71 inches tall, and Marin would also be 71 inches tall. So they're both 71 inches tall after 2 years. So will Bergen ever be as tall as Marin? Yes. If so, after 2 years. How tall? 71 inches. If this continues, by the time in 2 years from now when Bergen's a junior, he's going to be taller than Marin. The book gives you some other nice examples here too, and I highly recommend you read through this. I don't need to go through it with you, but this is the example of two airplanes traveling and where they're going to meet or where they're going to cross. The next thing I need to show you is this idea that when two linear equations meet at one point, there's called one solution. And you'll notice they have different slopes. So this red line has a negative slope, this blue line has a positive slope. That means they're going to cross at some point. If two equations or lines have the exact same slope, I should go like this, whatever, they're never going to touch, which means there's never going to be a solution. There's no solution. And in this third situation, If you end up having the same exact line, for example, y equals 2x and y equals 2x, these lines are the exact same equation, therefore they would graph directly on top of each other, and no matter what you plug into one, you plug into the other, you're going to get the same output in both. In that situation, there is an infinite number of solutions because no matter what you plug into one equation, you plug the same thing to the other, and you're going to get the same output in both equations. So what happens when you are given these equations? The first thing you need to do, so in this example, we've got negative x equals negative 1 plus y, and x plus y equals 4. It says solve the linear system by graphing, and then check your answer. The first thing you need to do is write these equations both in the same form, and I'm recommending slope-intercept form. So you can see here in this first one, I'm getting y all by itself, right? I'm adding 1 to both sides, so I can end up with y equals negative x plus 1. Because I can graph that. I can look at this and go up 1 and apply a slope of down 1 over 1, down 1 over 1. Same thing with this x plus y equals 4. If I subtract an x from both sides, I can rewrite it as y equals negative x plus 4. Now look, when I graph these out, you can see this first equation, I go up 1, and the slope is down 1 over 1, down 1 over 1, down 1 over 1. When I graph this equation over here in blue, it says go up 4, right? Here's your y-intercept. And the slope is negative 1, down 1 over 1, down 1 over 1, down 1. Well, guess what? Whoa. These lines are parallel, therefore there's no solution. When I go back in and I can check this, since both of these expressions are equal to y, right? Y equals negative x plus 1, or y equals negative x plus 4. Well, y is the same as y. I can set these expressions equal to each other, and I'm literally doing that. I'm saying, hey, negative x plus 1 equals negative x plus 4. If I add an x to both sides, 1 does not equal 4. It means it's never true. There's no way that something I could plug into the first equation will be the same as the second equation. So that's the big idea. Again, you can see this example in the book. There's another example B that goes along with it. I recommend you look at it. So here's your assignment. Page 8.6, page 370 to 71. It's only 6 problems. Some of them will take you a little time. You know there's graph paper on my desk. If you have a question, please email me. I'm going to try to go back to bed, but I'll be up and about. You know what I mean? And I hope to feel better tomorrow. We're going to do some quiz corrections tomorrow, do some Khan Academy. If you're done with all this, please work on your Khan Academy. Be good to one another, and have a good day.